All right, so now we move on to question 7. So question 7, 8, and 9 no longer deal with the example that we had above where the actual water vapor was 5.2. Now we're moving on to something else, okay? So they say, if a parcel of air at 20 degrees Celsius had a relative humidity of 40%, how much actual water vapor would that parcel contain? So I'm not going to do it for you, but I do hint that you have to use the equation that we had before. However, in this case, you know the relative humidity, so you know RH, and you have an idea of what the maximum water vapor capacity is based on the temperature that they give you for that parcel of air. So basically, if you find out what the water vapor capacity is at 20 degrees C, and you input that down here, and you have the relative humidity here, you can solve for the actual water vapor in the air. So you would just say, instead of this formula, you're going to deform it a little, and you're going to say 100 comes to divide over here. So let's just rework this a little. And then the maximum water vapor capacity is going to come to multiply to leave the actual water vapor alone. So and this up here will be actual water vapor. So that's how you're going to solve it, okay? All right. So now we move on to question 8. So question 8 says, what would be the dew point of that parcel of air? So remember, the dew point means that it's at saturation. So the air can no longer hold any more gaseous water, right? Any more water vapor. So being that what it is, what does that mean that the relative humidity will be? So I'll let you think about that. Okay, so now that you have figured out what the relative humidity that you should be using for number 8 is, right, based on just connecting the dots, and you know what the actual water vapor is based on your calculation from number 7, you can figure out what the temperature will be based on the values that you have on the table. So one of those values is going to match the value that you got in number 7, so that your equation becomes basically just 100%, which is what your relative humidity is. Oh, sorry, I skipped over all this stuff. So again, you're solving kind of for the maximum water capacity in this case. So this is going to be your actual water vapor, which you got in question number 7. And this is going to be your relative humidity, which again is going to be at dew point. So that should help you out to figure out what it is. This is question 7. Okay, so once you figure out what this is, what this number is equivalent to, you can use the table to find what temperature that number belongs to. Okay? All right, and number 9 says, if the amount of water vapor stays the same, but the parcel warms to 25 degrees Celsius, what is the new relative humidity? So this question here gives you 2 pieces of information. The first one is that the temperature that you should have obtained in number 8 has to be less than 25 degrees C, because this parcel of air warmed. So that's one kind of checking point. But the second thing, what it is asking you is that now, using this formula over here, you're saying, okay, now the maximum water vapor capacity value that I use has to be the one equivalent to 25 degrees Celsius on the table. So you're going to go over here and you're going to say, okay, my value for water vapor, maximum water vapor capacity at 25 degrees C is 23 grams per meter cubed. So that's the value that you're going to use. And then what you are trying to find out is the relative humidity. So you're back to basically using this formula up here. You're going to say relative humidity is equal to whatever number you got here for question 7. And then here, that number that I just showed you times 100 gives you the relative humidity. Okay, so that concludes our brief overview of part 1. I'm going to move on to part 3 and 4 before I go to part 2, since part 2 is all for the extra credit part of this lab. Alright, so now we move on to part 3, which is global air masses and fronts. I'm going to go ahead and skip through the beginning part. It talks about fronts and about how basically you go from high pressure gradient to low, or high pressure to low pressure as a pressure gradient as fronts move, so on and so forth. So on May 3rd of 2010, eastern Washington and northern Idaho experienced a severe windstorm that included sustained winds of 40 miles per hour and wind gusts of up to 80 miles per hour. These strong winds not only resulted in property damage, but also a dust storm that created additional hazards. Surface weather observations are gathered from broad geographic areas in order to paint a picture of the geographic patterns of air masses and frontal boundaries. These observations are also incorporated in weather forecast models. So here below you have a map of sea level pressures for the region of 1 p.m. or the region at 1 p.m. And I believe it's a specific time on May the 3rd of 2010. So here you want to create a weather map that includes the following things. So this beginning part says draw the contours of pressure surfaces, otherwise called isobars. So I'm going to show you how you're supposed to do that. I think in the lab I also have a help aid as to how you're supposed to do that. But just in case it's a little easier for me to show you, I'll do that. I'm not going to show you where to mark low and high pressure or put lightly shaded areas or the raindrops. That should be all up to you. But I'll show you how you should start at least to draw the different isobars. Okay? And that's what you're supposed to scan and later submit onto the file response on Blackboard. Okay? Alright, so this is your map. This is what you have to work with. These are the different pressures that we're taking throughout the country, throughout the northwestern part of the country on May 3rd of 2010. So let me get you the map so we can show you how that is done. Okay, so I'm going to use PowerPoint here. You can print off the map and use just pencils to do it, but you're also free to use whatever tool online you prefer if that's something you want to do. So I'm going to insert a shape, use a curve. Okay, so the first isobar, or the first pressure line that we want to draw, or isobar, is the one of 992 millibars, okay? So now we have to find points that are nearby 992. So if we look down here, we don't see anything. Everything's above 1,000. Same here on the right. Anything that's 900 or, well, below 1,000, it's up here, somewhere in southern Canada, northern Montana, basically. So let's see. So we have 992.5, so we want something a little bit below that. 992.1, so a little bit below that. But those are the only two measurements of 992, or close-ish enough, that give us an idea. So we know that the line has got to be lower than those two values, and we see that it's progressively getting greater. It's increasing in pressure the further away you get from that, so lower has to go towards Canada, basically, in this scenario. So basically, you make a few points. We don't know exactly where the line's going to fall, right? It's not going to fall right on the point, because those points are not 992 per se. Well, and I messed up a little here, but that's good enough. Okay, so there's our first isobar. Okay, so the next one is 996. So we do the same thing. So we locate any values that may be close enough to 996, or that limit between 992 and 997, 98, and we draw the line in between them. So here's a 996.5. So between 992.5 and 996.5, you have 996. Clearly, it's closer to the 996.5 than to the 992. So when we draw the line, we know that it's less than 997, so it's going to go probably around here. Close, but not quite touching the point of 996.5. Really close to 996.3, but not touching the point. Greater than the 994, right? But less than 997. Still closer to 997.3 though. So draw it in between. Let's see, it's pretty much right in between 994 and 998.3. So right in between them. It's closer to 994 than to 1003. So we'll just keep it going like this. It's less than 996.2, so we gotta move it like that. Alright, close to 996.7. And that's pretty much all the values that we have to help us with that. So we finished that line. So that's our next isobar. Alright, I'll do one more for your sake. So the next one is going to be of 1000 millibars. So same thing. Sort of curve here. So let's see. So we need to locate values close enough to 1000 that will limit the range of where we find them. So here we have 997.7. Here we have 1001.8. So the value is going to go somewhere in between. Okay. So you see, for all of these, I'm putting them closer to the 1001 than to the 996s or 97s that we have, because the value of 1000 is closer to that. Here's really close to this 1000.6, really close to 1000.9. Not quite as close as 1003.5. So here we'll go in between these values, in fact, like that. But we know that it goes in between these two, so we'll do that. Let's see, it goes in between these two values like that. Okay. In between these two values, closer to this one. In between these two values, still closer to this one. And that's all we got to guide us for that isobar. Okay, so it's coming along. So you see that there is a pattern sort of for this specific map and for this specific day that we have going on. One thing about isobars is that they will never touch, so you will never go from a pressure of 10 or 1000 to a pressure of 996 right next to each other, or like literally touching. That cannot happen. There's always going to be a gradient. Pressure always goes from something to something. It doesn't just suddenly jump, however many millibars. You're going to have to see a gradient, however small it can be. So granted, here, for example, the gradient is very small, like very small space, but there's still some space, so they're not touching. Okay, so your isobars should never touch. That's one of the rules. You can have like concentric circles for some of them, like if it pinches out, you can do that. That can happen, but they will never touch, or they will never simply just end like this. What I did here in the map shouldn't happen. In fact, I should have, kind of finished it, but it takes a little bit of time, so I'm not going to go ahead and do it right now. But you understand what I mean. Okay. So once you have finished this map and then finished the other things of putting the low and high pressure letters, adding the shaded areas, and then placing the raindrops wherever you think there could be precipitation occurring due to the pressure gradient, then you're good to go ahead and either scan your map if you did it by hand, or take a really, really good picture of it so you can upload it, or simply just save the file if you did it through a tool like I just did, for example, and then later uploaded. Okay, so now let's go ahead and look at the questions based from that.